Hi, this is Tim. In this video, we're going to continue learning about motion control. So far, we have connected a servo simulator to our PLC so that we can simulate signals to our high-speed counter in both the positive and negative direction. And then we configured our high-speed counter so we would get a rotary indication of where we're at. But typically, most applications aren't simply spinning. Usually we are turning that into some type of linear movement. So in this video, we're going to go through this diagram. And yeah, go ahead and put in the comments about my crude drawing. But in a typical application, you're going to have a motor with an encoder somehow connected to it. And then there will usually be a gearbox. And in this case, we're just going to call this a 10-to-1 gearbox. And what that means is that for every 10 times the motor spins on this side, our output is going to move one time. And then somehow it's going to be coupled to something. And in this case, we're going to couple it to something and make it go from 0 up to 100. So let me put that down here. So our gearbox is going to be 10-to-1. And then actually to make this calculation, we're going to need to throw some value on this. Let's make this a 4-inch pulley. So our goal in this video will be to take our circular motion that we're measuring off of this encoder, calculate what that circular motion will be through our gearbox, and then take it to this linear motion right here. So instead of saying that we're somewhere between 0 and 360 degrees, we can now say that we're 0 to 100 millimeters, inches, or some distance measurement. Now, if you're coming into this video and you haven't seen the rest of the series, look down in the description because this will be one that'll be really difficult to just jump into. In our previous video, we've determined this rotary position right here, and that is the position from 0 to 1023. And every time our Z marker came up, we were resetting. Well, in a linear type application, you usually will not do that. So we are going to disable that. So let's go ahead and go offline for this one. Actually, no, let's do this one online so that I can make sure that you don't run into a pitfall. If I just go right now to my embedded counters and I go to my counter configuration, right now we need to uncheck this preset on rising Z. And that'll make this counter just count forever. The trick is, if I do this right now and then hit the apply button, it's going to fault the processor because the counter is enabled right now. And this can be a real headache once you get it faulted. In fact, I probably should make a separate video because I don't want us to get lost in that right now. So one, let's cancel out of this. And then let's go to our controller tags. And let's scroll down to local:3:0 and find that CTR0EN. We're going to make that a 0. And now we're going to open up our embedded counters. And we are going to go to our counter configuration tab and uncheck that preset on rising Z. We'll hit OK, and it's going to warn us right there that, yeah, we can really mess some serious stuff up by doing this. So read the warning. We click yes. And now we can re-enable our counter. And if we go down to our counter value now, we can see it's going up 700, 800, 900, 1,000, and it did not reset at 1023. It is going to keep on getting it. And so now we're going to have to externally reset it, but we'll get to that in just a little bit. We need to take this big number that right now is accumulating and turn it into something that we can understand. And we're going to do it by doing some math on our layout here. So right now we know that every turn of our motor is 1,024 counts. So our value divided by 1,024 is going to tell us how many times this motor has rotated. So let's take this one step at a time. Let's go to our main routine and let's add a compute instruction. And first our destination, because we already configured it in our HMI, is going to be linear position. And that is going to be our local :3:I, and let's scroll down and find that CTR0 current count. So that divided by 1024 is going to give us our revolutions that our motor has made. So let's put that in there so we can see that. Now we've done, here's 16 revolutions, and we can see it's actually matching this. It's going around, we're coming up, and 17 revolutions. So that is how many times that motor has rotated. So next on ours, we had this gearbox, and that's 10 to 1. So that means that it takes 10 spins of this motor to actually get 1 spin of this gearbox. And you'll see this a lot of times. One, to get a process slowed down maybe where it can't go 200 miles an hour, but also so we can use a small economical motor and get a lot of power out of it. It's like putting your car in first gear compared to being in fifth gear. But so that 10 to 1 ratio will be a divide by 10. So let's edit our rung. And right behind the divide by 1024, let's put divided by 10. Now also here, I could just put divided by 10,240. I could make one big bulk multiplier. But later on, when I'm trying to break this down, I'm going to be able to figure out what the world this meant. Well, let's put that in there. We're showing 2.5 revolutions. So that means for all this spinning that this motor has done over here, we've only turned 2.5 times over here. Now here's where it can get a little tricky, is now we're going to take this rotating motion and we're going to turn it into a linear motion. And to do that, we need to know what the circumference or the distance around this wheel is. Because this wheel, if it turns 1 revolution, it's going to cover the total outside distance of this wheel. And to get that, we're going to multiply the diameter times pi. Now, I already stated here the diameter would be 4. We go in here and edit our program again. In this case, we're going to divide by 4, and we're going to divide by 3.14, which is pi. Now, honestly, for my mental check-in state here, I probably wouldn't do it this way. I would actually probably put some parentheses here and do that 4 times 3.14 and put it all in parentheses. It's going to do the same thing if you follow order of operation. But just when I'm looking at this, it's going to be a lot clearer here that, okay, 1024, that's going to be my encoder count. I'm going to see this 10, and I'm not going to know immediately what it is. But then 4 times 3.14, I'm going to immediately know, okay, that's probably a diameter. So let's put that in there. Now we have an actual distance. With all of our counts and everything, we have moved roughly 0.3 widgets or units. Widgets are parts, yeah. Units are distances. And okay, well, there you go. I wrote 4 inches there, so we're going to be operating in inches. So we have moved 0.3 inches so far. Now on our scale over here, we're 0 to 100. So it's not showing anything yet. So now let's get some movement into this thing. Let's go ahead and change our analog value, which we made in our previous program. Right now, our analog command is 10. Let's make it 100. That way we get some movement into this thing. Okay, and now we're moving faster, but we're not moving really fast. Well, first, what is 100? Let's make sure we understand that. Is on our analog, we're showing roughly 1/10 of a volt. Now the scale of our servo is 0 to 10 volt. So we're only running 1% speed right now. So that's what you're seeing here is this thing is creeping insanely slow. So let's go ahead and make it 1,000. Okay, and as crazy as that looks, that would be kind of representative of our motor spinning. And now, all right, we're starting to come up on the scale now. See, we're showing a little value. And if we go into our program, then yeah, we have moved 3 inches. So on our scale of 0 to 100, all right, we're slowly moving. But again, we're only running 10% speed right now. So let's go ahead and change this to 10,000, which will be our maximum speed. All right, now we're moving pretty good here. So now let's make it where when we hit, let's say 50, then it'll go back to 0. And we're just doing some crude stuff here because mainly I just want us to work out the linear math and get just mentally in our head visualizing this linear positioning that we're doing now. Is let's go back to our PLC program and let's put in another rung and let's start with a compare and a greater than instruction. And we're going to put if the linear position is greater than 50, then let's move minus 10,000 to our analog command. We'll put that in. Okay, so it was already at 50 when we did this. And yeah, this is a little difficult to tell what's doing now because it's moving so fast, but we can see now that we are heading back down in the negative direction. So now while that's going on, let's copy and paste that rung. And let's change our greater than to a less than. And let's change our source B to our 0. And then for our move, let's make that a positive 10,000. And actually, just so we don't have to wait so long, let's go back in there and let's make source B 25. So this way, if it's below 25, it's going to put a positive 10,000 in. If it's greater than 50, it'll put a negative 10,000 in. Okay, now it's heading down. We can visually see it, and we're at 25. All right, and right away it switched, and now it's going up. All right, it's about at 50. And now it's going back down. So that gets us from this spinning encoder into something linear where we're actually able to position something. Also using the servo simulator, we were able to visualize this on the screen. So in future videos, we're going to talk about how to move to a position, do some action, and then maybe move back to a position. So maybe this is a station that's out of the way on an assembly line, and it gets to where it needs to do something. It goes out, does some action, retracts back, and lets the part go on. So I hope this video has been helpful. I'll put links to this Compact Logics PLC trainer and the PLC Tools Servo Simulator in the description. Till next time. Hi, this is Tim.
And this is Amber of TW Controls. We run the automation store. Hey, thanks for finding our channel.
Here's a playlist with some similar videos.
And YouTube thinks you'll like this video.
Please like our video and subscribe to our channel.
And if our videos have helped you make some money and you're not using our products, please consider supporting us on Patreon.
Till next time.
See ya!